All right. Good morning, everyone. How are you all doing? Good? Good? Okay. Does anyone have any questions before we get started? So we still have about half the class who hasn't responded to the mid-semester feedback survey. So please do that by today. And basically, that we're just going to summarize it by the end of the day today. It'll just be what it is, and that'll be the voices that we have compiled. But I would like to hear all of your voices. So if you haven't done it yet, please do it. Like I said, you can spend just like 3 minutes on it, and you can do it really quickly. All right. So we left off with this example, and we had said that we looked at our reagent. Our reagent was that hydroxide. So hydroxide, because it was the O-, was a strong base, strong nucleophile. So that told us that we were going to do E2 or SN2, because the really reactive reagent is going to react right away. So it's not going to wait around for a carbocation. It's going to immediately attack either a carbon or a hydrogen. Our substrate is a secondary leaving group. So we know it's secondary because we have the leaving group attached to a carbon, attached to 2 other carbons. So secondary didn't really help us. That was telling us that we're doing either E2 or SN2. It doesn't really help us that much. So what we need to do is look at our temperature. So remember that solvent was what helped us pick between 1 and 2. So if you're comparing like SM1 to SN2 or E1 to E2, then you use solvent. If you're trying to pick between E and S, you're trying to pick between elimination, substitution, we use our temperature. And I had said that for the sake of this class, we're just going to say room temperature is going to favor elimination. So for room temp, we're going to say it's E2. So that told us E2 is going to be our major pathway. So looking at this, because of the fact that we are comparing elimination to substitution, now we get major and minors. So the last 2 examples didn't have major or minor, I don't think. Well, I guess we did have minor pathways for our elimination. You get the other alkenes, but we didn't have like the substitution versus elimination. So with this, what it's telling us is E2 is our major, and SN2 is the minor. We will actually get both products. It's just that we're going to get way more elimination than we will the substitution. When we go to consider our regiochemistry, for our regiochemistry, what do we need to look at for elimination? Regiochemistry, remember, that's picking between the left and the right side, which region is attacking, which hydrogen do we take. So what do we need to look at to know which side we attack? Yeah. So we would need to figure out, do I have beta hydrogens? That's the big thing, is if you don't have beta hydrogens, then it doesn't matter. So I look here, and I have 3 beta hydrogens here, because that's my alpha carbon, there's beta. And then I have 1 beta hydrogen here. So I do have a left and a right side. So what is going to determine which side I attack? How do I know? Yeah. How bulky the base is. So hydroxide, is that a bulky base? No, that's really small. If anything, it's only 2 elements. It's tiny. So that tells me I'm going to attack my more substituted side. Why did I attack the more substituted side? Because I didn't need to worry about sterics. So if I don't need to worry about sterics, I'm going to make the most stable alkene, right? Now the stability of the alkene was more important, which was that thermodynamic argument, right? So if I take from the less substituted side, that happened quickly, that was kinetic. But taking from the more substituted side, that is thermodynamic. So regiochemistry, we had said a non-bulky base. And so then that told us we're going to make our more substituted alkene. And what word do we use to describe that? We had Zatsev or Hoffman. Which one? Zatsev. Good. For our SN2 reaction, for our minor product, what would be the regiochemistry? Where do you attack when you do the SN2? Yeah, the backside. You're going to attack that alpha carbon. Right, you attack the carbon that has the leaving group. So the regiochemistry where you react is going to be that carbon with the leaving group. You attack that exact carbon for SN2. All right, so now we're going to do our stereochemistry. Stereochemistry is that cis-trans EZ. So for our stereochemistry, what do I need to do? How do I know if I'm making the E or Z alkene? Yeah. We need to look how many hydrogens are on the beta carbon. So I redrew it down here for us. We said that we're taking it from this left-hand side, the more substituted side. So what does that tell me? If there's only one beta hydrogen, how do you know it's going to be trans? Well, it wouldn't be trans, it would be E, but how do I know it's going to be E? And actually it isn't E, but why do you think E? Well, no, so sorry, that was a really, I didn't mean for that to be so aggressive. Yeah, I meant, sorry, it was just each time as I was talking, I was like, oh wait, no, that isn't that. And so that was like me correcting myself. So, but why, how did you get there though? Okay, I love it. So that's, yeah, so you and I, we just did the same corrected pathway where you and I both saw that like, oh, all right, that methyl's on the opposite side, but technically the ethyl is bigger, so that would be high priority. So they're gonna be on the same side. So it's actually, that's why it's Z. But yeah, so what we're seeing is this hydrogen has to be 180 degrees antiperiplanar from that chlorine. So what I was teaching you was that you need to do the Newman projection, right? It was, because you got to make sure that it is 180 degrees to be confident. So the Newman projection was that useful tool that reinforced it for ourselves, like convinced ourselves that yes, I am 180 degrees. So let's go ahead and use that tool to be confident about it. So if I'm on, let's do the right side. We always do the left side. So here's my little body. So if I'm on the right-hand side, I get my circle and my dot for my Newman projection. All right, on that front carbon, is my line going straight up or straight down? Straight up. It's above my head, so it goes straight up. How about on the back carbon? Straight up or straight down? Straight up. So it is also going to be above my head. So like here's my head is up here. My feet are down here. So that means that this is eclipsed. So I finish out my Y, I get my upside down Y. That means that I have my methyl is up there, my ethyl is there. So to the chlorine, is that chlorine, could you, oh no, was that your iPad? Okay. Okay, all right, cool. You have more faith in Apple products than I do. For chlorine, is that going to be on the left or the right? Should be the right. If I'm on this side and I'm looking at wait, this side. If I'm looking at it that way, into the plane is on my right-hand side. And that's my front carbon, so it's got to be coming off the dot. And then the hydrogen is what is to the left. All right, so then where is this methyl going to be? Left or right? On the right. So the hydrogen is there. So technically, because we're in the eclipsed conformation, technically, this hydrogen is not antiperiplanar to that chlorine. So in order for it to be truly antiperiplanar, it actually should be on the lines. So that's part of the reason why when we were looking at our chair conformation, it was like it had to be axial, like it's got to be on the line is kind of a way to think about it. So we need to rotate this. You can either rotate the front carbon or the back carbon, whichever you want, but you need to get this hydrogen to be opposite that chlorine. So I'm going to rotate that hydrogen clockwise. So that it becomes staggered. So everything just shifts a little bit. Now, it truly is antiperiplanar. So when I go to remove those, I see that I end up with my methyl is in that upper left, ethyl is the upper right, the methyl on the back, like down here, is the lower right, and the hydrogen is over there, right? So it's like that, where you think about it is this way, because we're drawing that double bond, ooh, come back, drawing that double bond right there. So then that's what gives us the stereochemistry of this product to see that it actually is Z. So the stereochemistry consideration was we had one beta hydrogen, means check the Newman. To know confidently that we're going to get the Z alkene. Because if you have one beta hydrogen, it could be E or Z, right? So that's how I know that that's going to be that stereochemistry, and that actually is my product. So if I wanted to draw it out up here, it actually is still that same arrangement of the atoms, where the ethyl and the methyl are on the same side as a line diagram. So what's interesting to note is we can take a shortcut. So the shortcut is that even though this technically isn't truly antiperiplanar, when we did that rotation, we didn't rotate it that much, right? We just did a little shift. So if I just do a little shift, what I can see is that I'm essentially just drawing in the double bond, and I shifted that methyl just to be up to become the line, so that I actually retained this same stereochemistry, right? So you see how it kind of just fills in the double bond exactly as where it was, because the hydrogen was the wedge, the chlorine was the dash. So because they're opposite, that meant that the line parts stay the same, and then whatever was a wedge or a dash would become the other lines. Does that make sense? How you can use that as like a shortcut, that basically you just retain the current carbon structure. If it doesn't, then do a Newman projection. So Newman projection will make sure you have the right answer. That's just a shortcut you can take. But watch out, if you're trying to do that shortcut, note that if they were on the same side, so if this hydrogen was actually on the dash and the methyl was on the wedge, a lot of students try to do the shortcut at this point, and then they get the wrong answer. Because in that case, you would need the opposite stereochemistry, because they're not on opposite faces. So Newman projection will always get you to the right answer. Cool. All right, so that is our major product for the E2 reaction. What does your minor SN2 product look like? Well, we did our regiochemistry consideration. We did not finish the stereochemistry. So for SN2, we had said that it was that backside attack. So we get inversion. Of stereochemistry. So when I go to do this minor product, I'm going to put everything in exactly where it was, because everything else is unimpacted. It's just the alpha carbon that I'm going to play with. So it's just that alpha carbon. So that hydroxide is going to come from the opposite face. So it's going to come and push out that chlorine. So that means that my alcohol ends up on the wedge, because that's an inverted stereochemistry. SN2, it still has to be attached to exactly the same carbon. It just came from the opposite side. So we can illustrate that by doing a wedge instead of a dash. Cool. All right. Do we have any questions about how to do that? How to predict our products between SN2, E2, SM1, E1? Feeling pretty good about it? Okay, cool. All right, then let's go ahead. That was the last one, right? Yeah. Let's move over to chapter 8. Talk about our alcohols. So with our alcohols, we're going to have a lot of the same stuff. We're going to have a lot of still substitution reactions and everything, but we're going to see that we're going to also get some redox reactions. So that's kind of the new thing in chapter 8, is oxidation and reduction of our alcohols. So let's start out by just revisiting some of the basics about alcohols, reminding ourselves how to name them. So our alcohol can be a primary functional group. If it is a primary functional group, you use that OL on the end, and that is your suffix. If it is a secondary functional group, we use that hydroxy out front. We classify our alcohols based on the number of carbons attached to the alpha carbon. So you go alcohol, carbon, how many carbons are attached? So 1 is primary, alcohol, carbon, 2 attached, secondary, alcohol, carbon, 3 attached, tertiary. And why, again, can there not be a quaternary alcohol? Yeah. Yeah, because I remember neutral carbon only makes 4 bonds. You can't make 5 bonds to carbon, and you need the oxygen to be one of them. So you can't have a quaternary alcohol because one of the bonds is the oxygen atom. So tertiary is our highest classification of our alcohols. And we want to avoid vinylic alcohols. So when we're talking about these, we want to keep this in mind. A vinylic alcohol, remember, vinylic means that you are attached to the alkene. That's our vinylic position, is that you are directly connected to your alkene. So another name for a vinylic alcohol is an enol. En for the alkene, ol for the alcohol. So it is an enol, meaning that there's an alcohol directly attached to that alkene. So this alcohol, and by the way, you're going to spend like 3 months of Orgo 2 looking at this. So in Orgo 2, you're going to have a lot of tautomerization, which is the process of going between your enol form, where you have the alcohol attached to the alkene, and your keto form, which is where you have the carbonyl. So the carbonyl is going to be the preferred form in general. So if there are no other factors at play, then that keto form, the carbonyl, is going to be more stable, because that carbon-oxygen double bond is stronger, it is more stable, it takes more energy to break it, than your carbon-oxygen single bond. So because there's so much more energy associated with this is way more favorable. That is the form that is preferred. So we want to avoid showing these enols because they're going to readily tautomerize to become a ketone or aldehyde. The exception to this tautomerization, to the keto form being preferred, is if you have something else there to help stabilize it. If there's something more stable than just having that carbon-oxygen double bond, such as having a full benzene. So another Orgo2 concept that you're going to spend the other month talking about is, why is benzene so special? And for now, I just want you to know it is. So benzene is going to be aromatic, which is essentially saying that we have this like double single, double single, double single. It is known as fully saturated. So, or not fully saturated, sorry. Fully conjugated, wrong word. So it's fully conjugated. That makes it aromatic. That is way more stabilizing. So if you can get a full benzene together, that is going to be preferred over just getting that carbon-oxygen double bond. So in general, we're going to say enols typically are not stable, and the normal thing is going to be, all right, turn it into a carbonyl. But if there's something else that's more stable, such as getting conjugation, then that's going to override that. So if you can have conjugation, you can get these like double single going on, that's going to then be preferred. So then the equilibrium will lie in favor of the conjugated form. Does that make sense? Okay. Just as like a pure basic introduction at this point. Okay. All right. Looking at our physical and chemical properties, our alcohols, when they are neutral, they are weak nucleophiles, which makes sense because they're neutral. They don't have a negative charge. So that made them weak. That's why we said the neutral oxygen went into that weak category. They're weak nucleophiles. Our oxides are going to be the bad leaving groups because they were the strong bases. The O- was strong. It was a strong base and a strong nucleophile. So that made it a bad leaving group because it just was going to become something more reactive. So we weren't going to kick out an O-. We said unless we already are starting with an O-. So if you're in extremely basic conditions, or not even extremely basic, if you're in basic conditions, so you already have an O-, then you can make O-, is the idea. So if you are in acidic or neutral conditions, in your mechanisms, don't kick out alcohols. You will need to activate them first. You will need to react with them, add an acid, do something else. You're not going to be able, you would protonate it first. You're not going to just kick out an OH. Basic conditions, if you're starting with an O-, then you can have an O-, then it's okay. So how we turn it into good leaving group is we activate. You activate it either with your strong Bronsted acid, so sulfuric acid, hydrochloric acid, hydrobromic acid are strong acids. Lewis acids, such as aluminum trichloride, boron trifluoride, so aluminum or boron, those are really good Lewis acids. Or turn it into a sulfonic acid. So use that sulfonyl chloride to make it the mesylate, the tosylate, the triflate, the OTF, OTS, OMS, those things. We can use that to make it a good leaving group. Our alcohols are also those polar protic solvents. So we need to pay attention to the fact that they can be both a solvent and a nucleophile and a base and an acid, and not usually an electrophile. They're not usually that one. But they're weak everything, but they are, that's why they can be used as solvents, is because they're not a great base, not a great acid, and not a great nucleophile, but they can be it. So we need to pay attention to that because that's going to be salicylisis, is where our solvent reacts. But we do see that because they're weak in general, they can be used as protic solvents. And that means that they're good solvents for SN1. And because we said protic solvents were really good at SM1 or at E1. So they are capable of doing hydrogen bonding. If we think about our different intermolecular forces, you have London dispersion forces, dipole-dipole, hydrogen bonding, ion-dipole, ion-ion. So hydrogen bonding was right there in the middle. In order to have hydrogen bonding, you need to have a delta positive hydrogen and a lone pair of electrons on nitrogen, oxygen, or fluorine. That's how you do hydrogen bonding. So the fact that I have a hydrogen on oxygen, hydrogen on electronegative atom, tick, I have a delta positive hydrogen, there's a dipole there, and I have lone pairs on that oxygen, tick, that is capable of doing hydrogen bonding, which tells me that it's going to have pretty high boiling points in general, because I have a strong intermolecular force, and as you increase your intermolecular forces, that increases our boiling points. when I look at these this kind of extension of that concept, where I have methanol, ethanol, propanol, butanol, pentanol, hexanol, all I'm doing is increasing the number of carbons as I go down. So as I increase the number of carbons, why am I seeing an increase in boiling point? What intermolecular force am I strengthening? Yeah, the London dispersion forces. Because I'm extending out that carbon chain. I'm not changing the hydrogen bonding aspect. Every single one of these have 2 lone pairs and 1 hydrogen. Every single one of these do exactly the same number of hydrogen bonding interactions. So the difference is just I'm extending out the carbon chain, that non-polar region. So I'm increasing the boiling point because I'm actually increasing my London dispersion forces. Because I'm extending that non-polar portion, the hydrophobic portion, hydrophobic meaning it's afraid of water, it is going to also be decreasing the polarity because I'm increasing the non-polar part, and therefore I'm decreasing the solubility in water because water is polar and like dissolves like. But I will be increasing the ability of the solvent to dissolve organic molecules in general, because now I'm getting this really polar head and a non-polar tail, so a hydrophilic head and a hydrophobic tail. So now it's really good at dissolving a whole bunch of different molecules. Cool. Do we remember all that Gen Chem stuff? Are there any questions about it? Cool. All right, let's try to remember our acid-base chemistry. So as we said, our alcohols are amphoteric, meaning that they're both acids and bases. They're not really good at either, but they can do both. So they are weak acids, similar to water. Y is, that pKa of water is wrong. pKa of water is actually 14 because we're taking it as the true gas phase. So looking at the 14 compared to that 15, why are our alcohols less acidic? Induction, yeah, thank you, yeah. So we see, when we talked about induction with our acids and base rules initially, we only talked about it from the electron withdrawing standpoint. We didn't talk about the fact that you can have electron donating. So if you have really electronegative atoms, they're pulling that electron density away. They're pulling it towards themselves. If you have atoms that are just hydrocarbons, you just have carbon and hydrogen, those are electron rich. They're going to push electron density in. It's not a true dipole. Well, it is actually a true dipole. They're pushing electron density towards that, which is destabilizing the conjugate base. So then that's going to make it less acidic because you have stronger base came from a weaker acid. But that also tells you that it, as the O minus, having that carbon there is actually going to make it an even stronger base. So we see that opposite trend. So as you go from your tert-butyl down to methanol, we have that increasing acidity because these are all pushing in, destabilizing that conjugate base that forms. The other secondary reason as to why our acids are less acidic is also due to solvation. So there's going to be some steric hindrance or some steric interactions that are decreasing the ability to do hydrogen bonding. So then it's not going to be as good of a proton donor if it's just a little bit harder to get at the proton, essentially, is what it's saying. All right, when we look at comparing our cyclohexanol to our phenol, why is the phenol more acidic? This one isn't written there. Yeah. Yeah, resonance. When you consider that conjugate base, for the conjugate bases, the phenol has resonance. So that's going to make it more acidic because it's a more stable conjugate base, right? So our acidity rules still apply, looking at charge, atom, resonance, induction, hybridization. They're also weak bases because I have a lone pair. I have a lone pair of electrons, so I'm capable of taking a proton. That lone pair of electrons is basic, but it's a weak base because when it becomes protonated, it generates that oxonium ion. It generates that strong acid. So it had to come from a weak base because it's making something that's positively charged. So this is going to be more acidic, so that is a weak base. So our neutral alcohols are both going to be the weak acid and weak base. It can do both, but it's just not very good at either. All right. Reviewing some of our syntheses of alcohols, we have substitution reactions. Why can't I make an alcohol from an elimination reaction? So you need a leaving group with elimination. What does elimination make? It makes double bonds. It makes alkenes, or alkynes, but so it makes pi bonds, right? So if I want to make an alcohol, I can't do it with a process that makes pi bonds because it just doesn't make the thing that I want, right? So don't overthink it, but that's why we're not going to talk about eliminations, is just because the elimination makes pi bonds, and we're trying to talk about how do I make an OH. That's not a pi bond, that's an OH. So it's going to be a substitution because I want to get a different functional group. So looking at our alkyl halide substitutions, why is this top one an SN2 reaction? Yeah. Yeah, so you have that strong nucleophile and it's that primary. You have a primary leaving group. You know it's primary because you have a leaving group attached to a carbon, attached to one other carbon. So that is really not sterically encumbered. And you have a nucleophile that's ready to attack right away. It's really reactive. It's ready to push that leaving group out. So yeah, that's absolutely going to be an SN2. Having both the strong nucleophile and a primary leaving group, absolutely going to be a great SN2 mechanism. All right. For the next one, why is this SN1? And I probably should have made it cold. Maybe not that cold, because then it's frozen. We'll do 5. Room temperature is about 20 to 25, so anything less than 20 is considered cold. What does SN1 like to do? How many steps are in the SN1 reaction? 2. What are the 2 steps? Leaving group leaves, then nucleophile attacks. So in step 1, leaving group leaves, what do you make? Carbocation. So if I'm trying to make a carbocation, why is that favorable here? Because it's tertiary. Having that tertiary carbocation is going to be more stable. So the fact that you have that tertiary leaving group, and then I emphasize the cold is going to be what's favoring substitution versus elimination. But yeah, you have a weak nucleophile, but remember, SN1 doesn't care. That 1 tells me all I care about is my one and only substrate. That's all that SN1 cares about, is making that carbocation. So that's what I care about. So the fact that it's tertiary, I'm going to make a stable carbocation. And then water is a weak nucleophile, so cool. It'll wait around for that carbocation to form, and then it'll react. Dope. We can also make alcohols from ethers, also doing a substitution reaction. So for this one, it is also going to be that SN2 reaction. It's SN2 because you're going to have a primary leaving group. So actually, I think it's worthwhile. Let's go ahead and draw the mechanism of this. I'll give you like a minute. Try to draw out your mechanism. Keep in mind what each of the reagents are that you have, and also think about where you're trying to go. So think about what bonds you need to form, what bonds you need to break. And whenever you get it, you can also then talk to the people around you, see if you have all the same mechanisms. All right. It sounds like most of us had had a conversation at some point, and I really liked some of the things I was hearing of like all right, this guy goes there, that thing will leave, that will attack. I really liked some of the keywords that I'm hearing of like, you're trying to talk about the flow of electrons. Love it. All right, what needs to happen first? What are we doing? Yeah, we're gonna activate. So, all right. So my clue is that I see a strong acid, right? Sulfuric acid, strong acid, it's gonna protonate something. You see a strong acid, protonate something. Something is going to take that hydrogen, right? So we're going to protonate our oxygen. That's going to be our most basic site. On exams, I'm cool with you doing one of two things. What I'm not okay with is you just writing a naked H+. Don't write naked H+, they don't exist. So I'm okay with you doing this kind of lazy way, which I don't know why this is like, I don't know, it's just not the hill I die on, but like, whereas H+ is. But the sulfuric acid, I'm cool if you just show the acid directly protonating your substrate. I'm all right with that. Technically, the way that lab does it is the more correct way, which is you have a lot more solvent molecules, so your solvent is going to probably protonate or get protonated first, not because of base strength, just due to just sheer volume. You just have so many more of your solvent molecules than anything else. So if you want to protonate your solvent first and then use that, cool. I'm all right if you want to use sulfuric acid directly to protonate it. Either way is correct as long as you have the arrows showing how you get there. So don't, what I'm also not okay with, so let's change to, we'll do orange. So things not okay on the exam is just doing a naked H+ and having your base attack. That loses points. Or just showing a reagent that I didn't give you. That also leads to sad faces. So you can use that sulfuric acid directly as a lazy shortcut. I'm cool with that. It's technically not the most correct answer, but like, you're recognizing that sulfuric acid is your source of protons, so I'm cool with you protonating just directly from the sulfuric acid. If you make that oxonium ion to use that as like a proton shuttle, cool, you gotta make it. You gotta show me how you made it because I didn't give you that. I gave you sulfuric acid and methanol. So either use the thing I gave you or make this and show me how you make it. Does that make sense? Okay. So only use things that you're given. That's also just in general true. Like, and I have to always write it as a rule on exams. Only use what's given. Don't make up new reagents when you're doing mechanism problems. Like, if you're doing synthesis, I want you to create reagents. If you're doing a mechanism, I gave you everything you need. Don't make up new things to make new products. All right, because we're doing Bronsted acid base, we have to have those equilibrium arrows. Bless you. And I'm going to show loss of that hydrogen sulfate. You can either write it as plus HSO4 minus or write minus HSO4 minus over the arrow. Either way, just acknowledge to me that you know that it was formed and we're just not going to do anything else with it. So now I've made a good leaving group. So what happens next? Yeah, now the methanol is going to attack. I already told you it was SN2, but I know it has to be SN2 because either way I think about this, if I think about this as my leaving group, then this is a primary leaving group, right? Or if I do it the other way, because it's symmetrical, it'll be the same thing. So I know it has to be SN2 because it's primary, and I can't make a primary carbocation that's aliphatic. So I'm going to attack I'll attack the right-hand side just because it's closer. So it has to happen all in one go. Nucleophile attacks as the leaving group is leaving, all in one step. And again, you can do equilibrium arrows here if you want. It technically is more correct, but I'm cool with you just showing a forward arrow just to show the progress of it. I don't care how you do it. It's just the Bronsted acid base that must have equilibrium arrows. So that makes our alcohol plus our new ether. And then to get to our final product, we would just use another methanol because it's our solvent to actually do the deprotonation. So this is also known as the transesterification reaction, meaning that I'm going from one ether to a different ether. Not esterification, transesterification? Whatever. We're going from one ether to another ether. But you also make an alcohol. So depending on which focus you want to have, if you care about the alcohol or the ether, both are formed as products. Cool. All right. Any questions about that mechanism? Did anyone get it completely right? No? Okay. That's all right. Yeah? All right. Keep practicing. Make sure you're paying attention to your arrows. You always start from where you have electrons, go to where you don't. Keep in mind that strong acid, you got to protonate something, you got to get a good leaving group. Once you get the good leaving group, then the thing with electrons attacks the thing that doesn't, except actually go to the atom to show that I'm making the oxygen-carbon bond. This arrow is showing that I'm taking the electrons from that bond and giving it to the oxygen, so I'm being very deliberate with those curved arrows. And then in order to get this to be neutral, all I gotta do is get rid of that one hydrogen. So I'll just use methanol to remove it. Okay, cool. All right, another way of making alcohols is to do ester hydrolysis. So hydrolysis, lysis means to cleave or to break. Hydro meaning water. So I'm going to break an ester with water. That is this step, is the ester hydrolysis. This is SN2. Or SN1, it doesn't actually matter. Both lead to the same product, but it's most likely SN2 in this particular case. So the benefit here is that I can have a good nucleophile, the strong nucleophile, that is not basic. So this is a nucleophile only. Because your acetate, if it takes a proton, becomes a carboxylic acid. Carboxylic acids are acidic. So it's not going to act as a base, it's only going to act as a nucleophile. So that's the benefit here, is that it ensures that I'm going to be able to use a strong nucleophile to replace this with an OH. Whereas if I just used hydroxide, I would get elimination. So that's the concern. So ester hydrolysis is a benefit, it's an extra step, but it prevents any of our elimination product from forming because I'm using a reagent that can't be a base. So I get to use an OH without starting with an OH, or without starting with OH minus. So the first step is that SN2. That gives us our ester. And then the ester hydrolysis is going to cleave this bond so that this oxygen is that oxygen. This oxygen is going to be, actually it's one of these, it doesn't actually matter. Kind of depends on concentration of your base, but it's going to be one of those. So if you're using isotopic labeling to do an O18 study, so if this was O18, O18, you get O18, O18, and you would see O18 incorporated into the alcohol. So you can use a radio label to track it to know where it ends up. Just like how you can use deuterium instead of hydrogen. All I'm doing is using an isotope. It behaves chemically the same. Remember, isotopes behave chemically the same, but have a different mass because they have a different number of neutrons. So I can use that label to like track where all the elements ended up. And then that would also still be O18 because that was from there. All right, so the mechanism of the actual hydrolysis, the mechanism you're fully capable of knowing, but I'm not gonna ask the mechanism on the exam. You do need to know this reaction. So if you know the mechanism, then the reaction makes more sense. Like you need to know that this is a way to get your alcohols. But the mechanism itself, this is not going to be a mechanism question, right? Like I wouldn't ask you this on the exam. Oh, we also forgot to actually write in the advantage was it avoids E2 by using a weak base. I said it verbally, but I didn't write it. That's the benefit of using that reaction. So the mechanism, because it's an orgo-2 concept, is that mechanism. It's carbonyl chemistry. So you won't be asked the mechanism on the exam. Still need to know the reaction, but I'm not going to ask you to draw out the mechanism. But knowing the mechanism helps you know what's forming and how you're forming it. All right. So let's think about this reaction. Zoom back out. So first, I have my ester. I can imagine the resonance structure where I end up with those electrons up on that oxygen, right? I have a polar double bond. So this is not a major resonance contributor. Like this isn't a resonance structure I would expect you to draw. This is just to think about the inherent reactivity. So this is to help you. We're trying to see that electrophilic carbon. You wouldn't draw this resonance structure. But what I see is that this carbon of the carbonyl is electrophilic. I see that's where I get that positive charge. So it's a formal positive charge with this bad resonance structure, but it's also going to be a partial positive charge here. So I can imagine then, okay, that hydroxide being a good nucleophile as well is going to come in and attack that electrophilic site. So we're going to do nucleophilic attack, and this would be addition, because you actually would be attacking there. And you'd be pushing the electrons up all in one step. So like that's the actual arrows. So this thing is just to help you see that your carbon at the base of the carbonyl, it's the electrophilic site. So this is addition because I'm going from pi bond to no pi bond, right? I have pi bond to no pi bond. Oh, and we will have to finish this mechanism on Friday. Cool. Have a wonderful day.